Start recording. So first off, did you get the opportunity to look at the homework? For homework for chapter 0?
No, not yet.
No, not yet?
I looked through it, and for question 1, there was like a lot of Lego questions.
Yeah, okay, let's hear them.
And it says we need to explain or answer.
Justify, briefly justify. I mean, in the textbook it doesn't, but I kept it in there because some of the stuff is
So we have to like...
just show your work, essentially. That's what it means.
Okay.
That's really all we're saying, show your work. What specific questions do you have about that one?
Like just how do we justify that? You just explain it.
Showing your work generally, showing that one thing is, you can either show like what happens when they get to ridiculously large numbers. You can show, although that's not formal, you can show that one dominates the other by just being bigger the formal way to do it. Okay. Actually, we can take a look at the practice problems 2. Take a look at 3. Okay. So let's take a look at problem 3 on there, where it says, given functions f and g, we say f is equal to O of g if there exists an integer c and n such that for all of n, all the n's bigger than that number, the professor who wrote this uses n prime and n instead of n naught and n, so just a difference in style. But they're saying for all the chosen numbers and for all these constants, there is a function that dominates the thing that t of n. So for instance, show that the following statements are true. 3n, all right, so we want to show that 3n, right, is bigger, is bigger than that. So that's fairly easy to do. I can choose an n equal to 1. Sorry, let me set n not equal to 1, okay? And then I'll set c equal to 5, okay? And now what we can say is that for, for every n, I think that's for every. I can't remember how to do for all. For all n greater than or equal to 1 now, we've got 3n is less than or equal to 5. 5n, right? So we've chosen a term, and we've shown that we've got a term that dominates it. So that's it's fairly straightforward on how to do it, because you've got a lot of freedom to just choose massive numbers for the thing you're trying to show what's big for what you're trying to prove.
So just choose a constant.
So you can choose some constants, and you choose a point at which that constant will always be true. And that can be all the way out wherever you need to. If the functions are, if you've got one function that's doing like wonky stuff like this, and another function that's doing wonky stuff like this, you want to choose it at the point where they stop flipping back and forth. That's very rare unless you've got some the only reason you'd get that is if you've got some wacky polynomials, But in some other cases like that, but that's like a typical example of that. All right.
Another question, like how do we do our work? Do we just write it down and skip into it?
Yeah. I'm fairly, for when it comes to turned in work, you can either turn it into me by hand, you can upload it, you can type it. I'm very flexible. I don't care.
Okay.
I care that I can access it. But that's a great question. I didn't really specify. That's why I let it have a link or a file upload. if you want to upload it to like your Google Drive or something and link that, or however you want to do it. Okay. So for problem 2 on that, so problem 2 on the homework, or 0.2 I should say, okay? That's a geometric series, right? So for that one, you're trying to prove that you're trying to prove something for g of n. Here, g of n is the geometric series, and that is, if I recall correctly, let's see, was it 1 plus, no, it's, sorry, here. I was just looking at it, but I always like to look to be sure. It's a very enforced habit. Yep, 1 plus c plus c squared plus c cubed, dot, 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 all the way to c of n. That's certainly a way to formulate it. Another way I've seen it formulated is basically, okay. Let's see. Wikipedia has another way to formulate it, but this has what's called a convergence, right? What do we mean by that? I mean there's a nice simple formula that this is equal to. If you don't know, you can check Wikipedia for how it derives. I don't expect you to derive it in this class. That's calculus 2's kind of domain, but you can see how to do those kind of things in calculus 2. All right. Any other questions? Again, and I posted another homework for chapter 1. I'll post them by chapter. It's 5 problems. Again, take a look at them over the weekend. Email me if you have any questions, or post the questions on Discord. That way, if it's something that you want to share with others and I can share the answer with others, I can.
On Discord?
On Discord.
With Discord?
There is a Discord. I didn't post it in this class. Great. Okay. Silly me. Okay, so let's go ahead and fix that. Announcements. I've done a very bad job of I need to fix this up. I've just had a lot of stuff that I've been trying to get done. I've been so focused on the material I forgot about like the basics of doing this. But yes, let me go ahead and Rosen's classes. Invite people. And let me go ahead and no limit. Expire after never. Generate. Copy. It is for, yeah. So this is for basically all my students, including the ones who are like done having me as a professor. Some of them still hang around. I've created a channel for every single class that we have. So yeah, if you want to just like communicate, the reason for this is that like a lot of students like form their own study groups, on chat and stuff. And sometimes, if you get a student who joins later in the semester, that means they've missed out on like that time to exchange information. And I figured I might as well just facilitate that a lot easier. Nothing stops you from DMing people or having personal conversations or setting up your own study groups. That's that's fine. But the difference is like via email. It's a lot more formal. Hi, Professor Rosen. How are you doing? I had this question. La la la. And whereas on something like a messaging system, it's a lot more like SMS, where you just simply shoot off a message and you're like, can I have an extension? Yes, or something like that. Or you might have a question and I'll reply with a GIF. It's a lot more of a, you're allowed, I feel like socially you're allowed to be more casual with those kind of things. So anyway, if you have any questions about the new posted assignments, or if I need to give an extension for chapter 1, again, they're from the textbook. Please let me know. Textbook question 5, we may not be able to get to today. Hopefully we can get to that. and if I need to set a separate due date for question 5, which has the RSA, which is an RSA question, we will. Okay. So I know we have 3 people registered for this course. So
Yeah, I don't know what happened to the second.
all right, I'll make sure that we can upload this. I'm not gonna wait any further though for this. So let's go ahead and GitHub. Not Classroom. GitHub. Teaching.
He just said he's gonna do it a little late.
Okay. Well, he's going to miss how to do addition, right? Like, I mean, that's so hard. How do you do addition? But seriously, we are actually going to have a serious conversation about these kinds of things. Now, I've got a question. How much hardware did you learn? Like computer hardware? Like, if at all?
For example, I think we.
Do you know what an adder is? All right. No, this is great because I get to go and lecture about things, and this makes it worth your while, right? I get to teach you new things. All right. So let's talk about let's start with a half adder, okay? Which sounds like it's a snake or something, okay?
Oh, yeah, we did this, kind of.
Kind of, right? When I had to do this, they actually made me, like literally program this, like in a simulated circuit as part of this. But basically, the way an adder works is that it takes two. This is how a computer does math. They have two. It has 2 inputs, or at least a half adder has 2 inputs. Okay, it has 2 inputs, A and B, that represent like a single binary digit, right? 0 or 1, and then it passes it into those inputs into a XOR and an AND gate, an exclusive OR and an AND gate, to figure out, okay, what is the sum and what is the carry, right? And so why an exclusive OR? Well, right, think about it. If you add 0 and 0, okay, so again, we're just dealing with adding 1s and 0s in binary. If we're adding 0 and 0, your output's going to be 0. If you're adding 1 and 0, or 0 and 1, your output's going to be 1. And if you're adding 1 and 1, right, no worries. If your output is, so if you're adding 1 and 1 here, okay, then you're going to get 1, 0, right? So that's why we have this XOR here for the sum over there in a half adder. And then with the carry, you only have a carry if both the things if you're only adding 2 1s together to get 2, right? So that's the half adder. So the reason I bring this up is because we need to talk about a basic assumption that we've been making, which is addition is, when we talk about addition, we often say, okay, if I'm going to do an addition operation, that takes constant time. Constant time to what, though? Because that's actually not true. It all depends on what we're counting. So we've been working in decimal notation. You've been working in decimal notation your entire time. For a lot of these examples, until we get to modular arithmetic, while we're going over addition and multiplication, it's going to be a lot easier if we do it how computers are going to do it, which is in binary. Okay, a lot easier. Don't worry about translating it, okay, into decimal notation. That's irrelevant for the purposes of our conversation. So you don't have to be able to convert it, but it just makes multiplication so much easier because you don't have to do any hard math. All right. So the larger the base, the bigger our base, the shorter representation is. But we don't really save too much time too much space by using a larger base. In fact, we have a formula saying if you're in base B, how many digits do you need to represent some number n? So like, for instance, let's go ahead and take a number that's a power of 2, okay, to make it fairly easy to calculate. Let's say, well, I say fairly easy to calculate, but I'm going to choose a fairly, oh, come on, what's going on here? I really have no idea why my pen is malfunctioning so badly. 250, you see that, right? just drawing and it's not going anywhere. Okay. What is going on? Okay, so boom, whiteboard. There we go. Okay, 256. There we go. Okay, so how many digits are needed to represent the number n? How many digits do we need to represent it in a certain base? Okay, so for base 10, I mean, obviously we're looking at it in base 10, we can see 3, but let's go ahead and just plug it into the formula. Log base 10 of 256 plus 1. So log of 256 plus 1 would be a bit more than 2, right? Log base 10 of 257 is a bit more than 2. I don't know how to do that calculation, but I know it's a bit more than 2 because it's not or it's a bit more than 3. No, a bit more than 2. Okay, so 256 and add 1 to it, and then we take the ceiling of it to round it up to 3. We need 3 digits, right? And let's go ahead and represent this one in, now let's go do log base 16, right? That's hexadecimal, right? If you know your hexadecimal, I believe that, this should be, 255 is FF, ain't it? Yeah, 0 to 255, right? It's FF. So 256 should be 100 in base 16 because, right?
Oh, yeah, okay, yeah, that makes sense.
Yeah, so that should be it. So also 3 digits. So if we do, so again, let's go ahead and calculator, good old calculator. Just try our stuff here. It's not going to tell us what the log, it's not going to let us define the log, is it? Oh no. Okay. Yeah, but we can check our math. Yes, 256 in hexadecimal is 100. And, the number of times that we can divide, but we can do this. The number of times we can divide it by 16 is 1, 2, plus 1 is 3. So 3 digits. Log base 2 for 256, that's going to require, this is, let's see, that would require, in log base 2 would require 9 digits, I believe. Because log base 2 is 2 to the 8th, sorry, 256 is 2 to the 8th, right? So, all right. But the point being here is that we're not going to gain too much when we change our bases, okay? When we change our bases, again, it's only going to change the number of digits by a constant amount. It's not going to change it by a linear amount, okay? So we're going to use base 2, again, because it's easier and it's simpler for us to build stuff in there. So, all right, so we've been doing this addition algorithm since grade school, okay? Which is that we take a bunch of numbers, we line them up, and go from one side and go from the right side to the left side, right? Okay, and that's pretty much how computers do math. Yeah, it points out there's a rule there, but there's a truth here that's useful in doing that. The sum of any 3 single-digit numbers is at most 2 digits long. Why is that important? So first off, we can show that's true in binary, and it's true in any base, but we can see here that if we add 3 ones together, that's going to give us 1, 1 in binary, right? So 1 plus 1 is 0, carry the 1. So 1 plus 1 is 0, carry the 1. 1 plus 0 is 1, 1, 1. So any 3 single-digit numbers is going to be at most 2 digits long. If we try that in base 10, the biggest, I'm going to try stuffing in the biggest digits I can. 9 plus 9 plus 9, that's 27. So again, that's 2 digits long, okay, in its respective base. So this is useful because we know that if we need to build when we build adder circuits, that basically they only need to take that they can take in 3 things. So a full adder takes in 3 things. It takes in input A, input B, which is either a 1 or a 0. And they also take in the carry in, which is what comes from the previous digit, or from the from the lesser place. And then then it's going to output two digits, which is the carry out, whether or not it had a carry, and its sum. Make sense? This is how computers, again, do math. And we simulate this over here by doing this math over here. So I'll go ahead and copy it over so we can actually do the math rather than just glancing at it and nodding along, which is, so let's see, 1 1 0 1 0 1 1 0 0 0 1 1. Okay, and again, just to add those things together in binary is very easy. Okay. Oh, I bet you I know what it is. It probably has to do with the voltage. It's slightly being slightly different in the U.S. and Japan.
On your pen?
Being plugged in.
Oh.
Because it's a touchscreen. It's messed with my laptop last time. It's not like harmful or anything. It just does some funky things every so often. All right, 1 plus 1 is 0, carry the 1, right? 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 0, carry the 1. Like I said, it's a lot easier to do this because it's either 1, 0, or, you've got 4 options essentially because it's binary with 2 options. Okay, so how long does this take a computer to do? Well, you'd think there'd be some funky stuff to optimize this, and you're right, there is, but in theory, really, it takes linear time. It takes O of n time to add things. But here's the important, what is n in this case? What is n? So how many operations did I do? I did 1, 2, 3, 4, 5, 6, 7. I did 7 operations. So it's linear to what? Then, well, what are the things I added together? Yes.
The number of bits.
The number of bits. N is the number of bits in this case. And a lot of times, and so why do I say it's constant to add 2 integers together, or why is it treated as a constant? Because when you're dealing with ints in Java or longs, those are a constant size. They're always 32, or they're always 64. And again, going back to Python for a second, Python gets to be awesome sometimes, and that's not to say there aren't bigger numbers than that. Python is notorious for just letting you do whatever the heck you want in terms of making big numbers. Because there exists, and Java can do that too if you use the big integer class. That's for doing stuff of arbitrary size. It's very useful to know that exists. But you can see that for addition, if we have giant numbers, that's kind of important to know that addition is not necessarily a constant operation. It's when everything's the same, it's great. Okay. So, and the rest of the slide just explains what I was talking about. We just simply add 2 numbers by aligning the right-hand ends. We go left to right. And again, they also mentioned that it's going to be, another way to think about why does this take a linear amount of time. It took us O of n time to write the first digit, O of n time to write O of n time to write the first number, O of n time to write the second number, and then O of n time to figure out each of the n characters. Okay, and again, here we were assuming that they were each n bits long because, that's basically our worst case scenario. They're both as big as each other. Okay. And I'm sure there's probably some funky adders that optimize stuff. I was looking at that up on Wikipedia. last night, and there seemed to be some implications for funkiness to go on. But for as a general rule, it's of O(n). Of course, got to be careful reading anything on Wikipedia. I'm just saying that that it says it's O of n, and we're going to say it's O of n for the purpose of the class, but don't be surprised if there's some academic kind of stuff that there's some partial speed up somewhere. All right, multiplication is very similar. So multiplication, again, this is, so 1, 1, 0, okay, so 1, 1, 0, so let's see how, so let's do multiplication in binary. 1, 1, 0, 1, 1, 0, 1, 1, right? Doing that by hand, it's a lot easier to do this by hand than like doing decimal digits. Again, we're working in binary because it's simpler. So 1, so multiplying this entire thing by 1 is very simple. Okay, then we do the tens the twos place, which is that's the twos place. So 1, 0, 1, 1 again, right? Now we multiply by the zeros place. So, or by the fours place, I should say, which is a 0, so that just simply zeroes out everything there, right? And then multiply by 1 again. 1, 1, 0, 1, 1. Okay? Now we just simply do we simply do an add operation. So 1 right over here. 0 and 1 is 1. 1 and a bunch of zeros is 1. 1, 1, 1 is 1 carry the 1. 1 plus 1 is 1 carry is 0 carry the 1. 0 carry the 1. 0 carry the 1. So it's 1, 3 zeros, 4 ones. So let's see if I got the right answer. 1, 3 zeros, 4 ones, which in binary apparently is the representation for 143 if you want to check your answers. So took us O of n time to write down, so these are each n bits, right? Same amount of, and again, worst case scenario, they're each as big as each other, right? If one was bigger than the other one would be smaller, so so it would be an easier problem. Okay? But there's n bits here, and so each of were n bits, and we did a grand total of n addition operations, right? We did n addition operations. Each addition operation takes how long again?
And
Oh, yep, it takes n. Each of those addition operations takes O of n time. So multiplication takes how long? O of n squared. And we always tell you that addition takes slightly longer than multiplication. Again, there's probably some funkiness that can be happening with circuits. I don't know. I'm not a circuits guy as much as I talked about that adder for a few seconds. But you know, you can probably optimize that at just a tad. Wait, actually, we know you can optimize it just a tad because we're going to talk about that in Chapter 2 with divide and conquer. That's not the only way to do addition, though, okay? And the reason we're talking about this is just to make sure you understand that stuff isn't constant time, right? These are basic operations where we've been saying they're constant time. They're constant only because we always use 32 or always use 64, okay? There's other ways to do this multiplication. This is the French way of doing there's a lot of different ways to do multiplication here, which is to do, and this is the method that Al-Khwarizmi used, and it's the method that a lot of European countries use, which is that you you write them down, and then you double them and have the other column. It's represented by this algorithm, which will follow because it is very useful for figuring out, we'll work through this algorithm. And it's very useful just simply because it's going to be a simpler thing to work through than some of the other stuff we're going to do. So, all right. So say I wanted to multiply together two things. Let's try 11 and 13 again. So here, when I do these kind of algorithms, by the way, I like to make a table, x, y, and z. Now, why am I making a table? Because if you notice, this is a recursive algorithm. So it's very useful to, when we're working with recursion, to make a table of where everything is at each depth. Okay? So here we're taking in annoying. Okay. Here we are taking in x and y, we are taking in and it says y is greater than 0, okay, and x is whatever. So it doesn't matter which one is which, okay? So I'll do 11 and 13. Okay, if y is equal to 0, return 0. Y is not equal to 0. So now we say z is equal to what we get back after we do a recursive call to x and y divided by 2. The floor of y divided by 2. So we're doing the integer division, essentially, of y divided by 2. Make sense? So here it would be 11 and y divided by 2, that would be 6. Okay, if y is equal to 0, return that. Nope, y is not equal to 0, so we do another recursive call. 3, do another recursive call, right? 3 divided by 2 is 1. And 1 divided by, and then y is still not equal to 0, so 1 divided by 2 is finally 0. Okay, so let's go ahead and let's go ahead and just divide those a bit better. Okay, so so we don't return anything over here. So it says, hey, 11 and 0. So if y is equal to 0, return 0. Okay, so now we've got him back. So now we're over here where we had x is equal to 11, y is equal to 1. Okay, and we just got back z is equal to 0. If y is even, return 2z. Otherwise, return x plus 2z. So is y even? Y is the second column. So this column over here, it's not even. So return x plus 2z. X plus 2z, so 11 plus twice 0. So now we do the same thing. We just got back z. 11 and 3 is 3 even. No, it is not, so return 11 plus twice of z. So that'd be 33, right? X, which is 11, plus 2 11s, which is 33. Okay, is y even? Yes, it is. Return 66. Okay, and now we're finally back at the top. Is y even? No, it is not, so return x, 11, plus 2z, which is 2 times 66, right? What? Did I make a mistake? Because I...
Oh, no,
sorry, 6 times 2. My bad. No, I should have been a lot more deliberate with that dot. Okay, so it's been a while since I've had to teach a math class, so that should be 230. That should be 232, right? That is 232 plus 11, which brings us to 143, which is the same answer as our previous problem. We've just done math a different way. This is actually pretty nice to implement in programming, because you can use the bit shift operation, right? Bit shifting allows you to multiply stuff by 2 or divide stuff by 2 fairly easily just by moving the bits to the left or to the right, right? Right, I can turn this number, which is in binary, that is what? That is 1, 2, 4, 8. So 8 plus 4 plus 2, 8 plus 4 plus 2, so that would be 14. I can double that by adding another 0 over here. That doubles that to 28. Or I could have that number to 7 by instead shifting over to the right. So makes it very useful. But still, shifting would take O of n time. Yes?
So for those two organisms you introduced, they both have like time complexity for unsquared, right?
Yes.
And like the Python multiplication show was too fast for unsquared, right?
I mean, it's n squared where n is the number of bits.
I mean like
Oh, when I was doing the multiplication over here?
yeah, or Python like that one.
Oh, when I was doing it in when I was doing it in Python where I had a really big number.
Yeah, that was too fast to unsquared.
With the speed of computers these days, I mean, the input size isn't that big for n squared, and computers run really fast. But yes, you're right. There are quicker ways to do multiplication if we do divide and conquer. There's a quicker way that we'll learn in chapter 2 to do multiplication. Yes.
Go. No, it's like a sidetrack. Okay. How are integers represented in Python again?
So how are integers represented in Python? Well, the answer is I'm not quite sure. I'm pretty sure they're ints, okay? I'm pretty sure internally they're ints until they wouldn't need to be ints, if that makes sense. Right? It would if I were to hazard a guess as to how things are internally represented in Pythons, they're ints until they need to be converted to longs, and then they're longs until they need to be converted into longs or something like that, or whatever the notation is. And after that, they probably use an arbitrary length class. I mean, it's a good exercise right now. It's a good exercise to take some time and think about, okay, if I don't have access to a class that adds big numbers together, how would I add numbers bigger than the maximum together? And the answer is probably by using a second number to represent the digits to the left. So you'd have the digits, one block of digits for adding to over here, and another block of digits over here. And you'd kind of pass them, and you'd kind of have to manually build an adder between those two digits.
How fast can be for like the algorithm nowadays for multiplication?
So let me pull up chapter 2 very, very quickly. Fast multiplication, okay? We figure out a form it can be written in, and there is a runtime analysis. So 1 to the point slightly more than n times the square root of n, which is not too bad. So there is a faster way to do it. It's not quite n log n, but hey, it would work. Similarly, division is a bit of a pain. So let's go ahead and take a look at division, okay? Division is, let's see. So division, again, is we're talking about integer division here, where we term things in terms, where things are represented in terms of quotient and remainder. So to divide an integer x by something that's non-zero, we figure out a quotient and a remainder where we have some multiple y that's multiplied by the quotient, and we add a remainder, and that's going to be equal to our original number. Okay. So example, it says x is equal to 2, x is equal to 5, y is equal to 2. You can probably up that, but again, the algorithm we can use for that is, again, we have two n-bit integers, x and y, where y is greater than or equal to 1. And the reason we enforce this greater than or equal to 1 is because it's not too bad to do if one is negative. We just simply would switch that around. We can switch that around. And if they're both negative, then obviously we don't have to worry about that because the result's going to be positive. So again, negative is for the hardware engineer, what it was for the hardware engineers to figure out, and do you remember what they used to represent negative numbers? Did you learn that in your hardware class or your systems level class?
And then start with 0.
Sorry?
And then start with 0.
I mean, so this is, we use all zeros to represent 0. I'm going to go to 4-bit numbers because that is easiest. Okay? But the question is, do you remember what this would represent in binary if we're dealing with negative numbers?
The biggest negative number.
Yep. It's 2's complement, right? What it was is that we thought is that we wanted our additions to be pretty easy. Simply put, like if we wanted to add, if we wanted to add 3 and negative 3, we basically want them to cancel out. So so we thought, hey, and just simply inverting them doesn't work. Well, actually, inverting them works just fine. They thought, okay, inverting them works just fine, and we call this 1's complement, right? Where we would represent everything where we represent negative 3 as the inverse. 1, 1, 1, 1. And this would represent anything, and we could tell the sign of something by the leading 1, right? So this would be the nonsensical negative 0. So first off, it's nonsensical. So it had 1's complement has 2 problems. First off, it's nonsensical. Second off, now we have 2 values representing 0, which is a waste of space, right? We have both a bunch of zeros and a bunch of 1s representing zeros. So instead we use 2's complement, which says we'll represent it by flipping the bits and adding 1. And what this effectively did was is that it much cleanly nullifies something because of the way this works. 1 plus 1 is 0 carry the 1, 0 carry the 1, 0 carry the 1, 0 carry the 1, but assuming we're just dealing with 4-bit words, right? This just simply gets tossed out into the void. It doesn't go anywhere. So that's how that cleanly adds out. And this actually ties very cleanly into modular arithmetic, where basically you just simply have a range of numbers you're adding to. But before we get into the modular arithmetic and dive into that, we are going to run through the example where we've got 5 divided by 2. And here what we're going to do is that we're going to do, so we need x divided by y, and the quotient and the remainder. I'll go over which of these, I'll figure out which of these algorithms I actually care about for you to do on exams, but for the most part I can guarantee you that it's the greatest common denominator is one of the big ones that I care about in terms of like exams or quizzes. I'll figure out what schedule it will be for doing exams and quizzes over this weekend. Again, I want the quizzes to be a bit more low stakes, check-ins kind of things. So anyway, x is equal to 0. So first off, let's check out how this works. So it says if x is equal to 0, well, it's not, but if it was, we'd return our quotient and remainder. Otherwise, we recursively do this. We divide 5 by 2 and pass down what we're dividing by, okay? So next, we're at this level. Is x equal to 0? No, it is not. So divide that by 2 and pass down this one. If x is equal to 0, return quotient and remainder equal to both, where quotient and remainder are equal to 0 and 0. So again, dash, dash, 0 and 0 over here.
Why is x a 0 again?
Because I did that, because I am terrible at math sometimes. It should have been 1, and then now we're here at 0, 0. Jump the gun there. I've been up since 5 a.m., so yes. Is there something you had a question or? Oh, okay, yeah, I thought you raised your hand. Sorry. All right, so now we're here at this point. We say, okay, return 0, 0, and so, sorry, return 0 and 0. We've got, so yeah, and what do we get? We get Q and R being that. And so now we say Q is equal to twice that value, R is equal to twice that. We multiply Q and R by 2. If X is odd, yeah, this may be easier to keep that. It's always, there's some justification as to whether you want to put the Q and R over here on the bottom or if you want to keep it on the row where you return it, because you're going to need to modify them. Just make sure you're consistent with whatever you choose. Q is equal to 2Q. So we twice 0, we get 0. Twice R, we get R. If X is odd, yes it is, X is odd, our remainder is equal to remainder plus 1. So now, and then if R is greater than or equal to Y, modify that, and now return quotient and remainder. So now quotient and remainder are equal to 0 and 1 over here. So Q is equal to, so when we double our quotient, double our remainder. If X is odd, is X odd? No, it's not. If X is, if the quotient is, if the remainder is greater than or equal to Y, subtract out Y and add 1 to the quotient. Okay? Now return now we return the quotient and the remainder. Now we're now back at the top over here where we've returned our quotient and remainder. Our quotient is equal to 2 times our quotient. So 2. And remainder is equal to twice our remainder. If X is odd, add 1 to the remainder. X is odd, so add 1 to the remainder. And then is R greater than or equal to Y? No, it is not. So now we return quotient and remainder. So now the answer is 2, remainder 1. And that's fairly easy to check, right? It's 5 divided by 2. It's 2, remainder 1. Okay. Again, so what is the running time for this? It's, again, quadratic. That's actually left as an exercise in the book. Let's see. And I don't know if I gave that one as a homework, but it's one of those things that we can, let me just check my notes here. I actually came prepared with notes for the day. Okay. So this one is, so each one of these is, so first off, you can prove this by induction. I'm not going to do so. That can be saved for homework or for a quiz kind of thing. But we can prove that it's true by induction, where you basically, assume that it begins, the base case is X is equal to 0, right? The number we're dividing by is equal to 0. That's the easiest thing to prove. And then in terms of just analyzing the runtime, we are, we're doing the divisions by 2, which is a bit shift to the right, and we're multiplying by 2, which is a bit shift to the left, right? So left and right, so we don't have to figure out what those are. Those are O of n operations. And how many of those do you have to do? So, and it should be like, well, you have to do n operations, each of which are O of n time. All right.
Are we expected to remember all the algorithms?
I will let you know which ones I care about. Okay. For your homework, you're expected to reference them, and honestly, I haven't even decided like if it's going to be OpenNote or not. So I'm a big fan of OpenNote. I think for math class it's appropriate to have an OpenNote because otherwise it's very easy to, under stressful circumstances, think, oh, it's a plus rather than a minus, a times divided by a times versus a division. So I'd be in favor of a cheat sheet, essentially as your notes. So. All right, so modular, so now we get into our modular arithmetic portion. we'll take a small break in a minute, but let's just talk about modulo arithmetic, which is going to be slightly different than talking about this symbol, okay? Which is the modulo operator, but I mean what that effectively does is it gives us, it gives us the remainder of something. Which is one of the ways we can talk about this. Modular arithmetic, as you've probably studied it plenty, right? Like in your math concepts class, no?
I think we did.
Okay. All right, so, right, but the big thing about modular arithmetic is that when we say that something is x mod n, okay, is that basically that there's some number that is a multiple of n, and then if you subtract, there's some number, and if you subtract n from it, it would be divisible. Or, that is here, that is x is equal to qn plus r, meaning that we have some number that if we multiply it by n and we add the remainder in, then then x modulo n would be equal to that remainder. So, or rather, if we add in this remainder here, if we subtract that remainder, it'd be 0. We're going to be using this notation a lot, by the way. X is congruent to y, mod n, which is a shorthand of saying that if you've got that these two numbers are congruent or equivalent, I'll be going, those two words mean the same thing, congruent or equivalent. Just know it's the triple equal sign, okay? We're saying it's not equal to. Equal to implies equals. It implies the same thing. Congruent means it's equals for the purposes of this discussion of the space. They're the same for the purposes of this discussion. X congruent to y mod n means that basically that, as it says, n divides x minus y. That means that, so first off, that notation, you might see it written as n divides with a big bar for for that divide sign. N divides x minus y. What that means is that x, if you x minus y is a multiple of n. Okay. Or you can just simply remember your computer science and remember that, it's remainders. It's all remainders, what we care about. Think about it. So again, the interpretations are, you've got the hands of a clock. You wrap around the hands of a clock as you add things. So let's see, it is 3:20. So 7 hours from now would be 10:20. But also 19 hours from now would be 10:20, right? Just flipping around, just PM rather than AM, we can add that as much as we want to. This is what's referred to as a congruence class, by the way, by your book, right? The idea here is that that we've got these so if my board. It means that, so let's talk about the space mod 3. That means that basically that we've got 0, 3, 6, -3, -6. Yes, we can deal with negatives in modular arithmetic. Don't get too scared about that. 1 and 2, 4, 5, 8, 7, -2, -1. I was worried I did the math wrong for a second. Right? And what we're saying is that basically that the space of mod 3 is divided into these. All of these numbers, -6, -0, -6, -3, 0, 3, 6, those are all congruent. They're all equivalent to each other in the space of mod 3, right? Because they can all be simplified down to 0. Similarly, 1, 4, 7, -2, -5 can all be simplified down to 1, right? They're all equivalent. That's why we call them equivalence classes, we can substitute any of them as need be, which is going to be really useful when we talk about stuff. Specifically, and let's see. So specifically, there is something called the substitution rule, which says basically if we've got some x and it's congruent to x to some other, basically if we've got two things in the same equivalence class, okay, and we've got two things in another equivalence class, okay, so we've got x is in one equivalent class, y is in one equivalent class, and we've got x prime and y prime, then we've got x plus y is congruent with x plus y mod n. Okay, so let's check that first statement. Okay, let's talk about mod 3 again. Mod 3. I'm the kind of person who likes to see stuff, right? So 2 plus 1, right, that's going to be equal to 0. You know, that's going to be equal to 0 mod 3, right? And if we replace these with equivalent things like 5 plus 4, okay? Those are both, 5 is equivalent to 2, 4 is equivalent to 1 in mod 3. That's equivalent to us saying, again, 2 plus 1 mod 3, which is, again, 0. And if you check the math, 5 plus 4 is 9. So we're saying basically that you can take shortcuts with addition if you need to. Okay? We can substitute that whenever we can substitute x and y whenever. Although we haven't fully justified that because there's some other, it's that you can substitute anything whenever you want to, comes from these substitution rules, plus the fact that we get our standard association, commutative, and distributive rules. The other rule, if we can do addition like this, is x, y is congruent to mod.
So when you do prime, it doesn't mean derivative, right?
Sorry?
It doesn't mean derivative, right? That's in prime.
It's just meaning a different, prime in this case denotes a different x, something in the same congruence class. Okay, and now let's go ahead and try this again, right? 5 times 3 is equal to our different x and y's. They're in different congruence classes. That's going to be equal to 15 mod 3, which is going to be equal to 0. Okay, and if we choose different things in their congruence class, but we could simply have always replaced the 3 with the 0, right, and shortcut it is what we're saying, right? We can reduce it. So the standard rules of associativity still apply. Let's see if we've got some slides on this. So I'm pretty sure we do, and I've probably just done them by hand. I think it works better if I show it by hand first, personally. Okay. Yep. So here's the rules that we were talking about. You also have your associative rules, which are x plus, which is basically that the order in which we add stuff doesn't matter, right? X plus y plus z is equal to x plus y plus z. It doesn't matter what order we do the multiplication in. 5 times 3 would be the same as 3 times 5. Make sense? And distribution, basically, so again, if we had, sorry, let's go ahead. 2 times 3 plus 1 is equal to 6 plus, it's congruent to 6 plus 2. Mod. Make sense? So it's just the same rules for regular addition here. The only difference is that we're wrapping around. There's a limited space we're working with. So the results of this, though, with the substitution rule means that it is legal to bring in our immediate results, legal to bring in any kind of simplification we can at any stage. So the way they show this is by doing this complicated modular arithmetic of calculating 2 to the 345th power mod 31. And again, they do this by going over to here, 2 to the 345. The way they do this is that they note that this is a power of 2, or it's a power of 2 minus 1. It's almost a power of 2, right? That can make our math a bit easier. So we get, for instance, so let's go ahead and just ask, what is 32? Is equal to 2 to the 5th, right? It's equal to 2 to the 5th. So we can extract out this by saying, we can rewrite this as saying, hey, 2 to the 5th power, okay? Divide this by this number by 5, 345. You can work it out, but I showed you this last time, 69. Right, and in order to do multiplication of exponents, you have to, raise the power, just as a reminder. And then, again, what we can do is that we can substitute this. That's, this is 32. 32. And what we're saying is that this is 32 times 32 times 32 times 32 times 32. Just done 69 times. And our substitution rule says we can just replace those with what it's congruent with. 32, so what is 32 mod 31? It would be, it's congruent to 1 mod 31. I'm trying to be good and not write equal signs here. So we can replace this with, so what we can do here is we can replace this with 1, and suddenly our math becomes incredibly easy. And the reason we care about this is that when we work with RSA, we need to do these very, very large operations. All right. Do people want to take, so I need to take a brief break. Everybody else feel the same?
Yeah.
Okay. Please let me know if you want, if you feel like when I finish something up, please let me know. I'm okay with I guess it would be time for a break. I'm okay with that, So I'm going to pause here and unpause this. And we'll say I was very excited. Yesterday, unfortunately, yesterday was not great. My yesterday was a lot better because I got to stop by the zoo, and on the way back, I had cold ramen. That was, and I was sweaty yesterday, so that was pleasant. Never tried that before. It was It was good. It was a lemon shoyu ramen. That was interesting.
You went to Ueno?
Yeah, it's good.
It's the famous one.
Yeah, Ueno Zoo. So let's talk about that. So there's some problems there on the first practice problem that I want to take a look at. All right, that we can immediately kind of figure out. Okay. Okay. So by the way, if you're curious, problem 5 is asking you to prove, the substitution rule. That's what problem 5 is doing. Okay, but let's take a look at one of the more solid ones because we just practiced that, which is question 6. Okay, question 6. Find 2 to the 1,744th, which I put up over here in mod 127. Okay? So, again, we can work through this. So I'll give you just a minute to take a look at it, but then we'll work on it collaboratively. Again, not a quiz over here. Just want you to think about it for yourself. And feel free to use a calculator to kind of do some of the basic arithmetic over here. All right. So what's kind of the first step that we should look at? Even if you weren't able to use it, what would be the first step that we would want to look at with this problem?
My first thought was you should put try to change it into where it has 2 to the power of 7.
Yeah, because now why 2 to the power of 7? That's exactly what we want to do.
Because that's 128.
Exactly.
Mod 127. So then if we can get to that form, it'll just be 1.
Right. Now, the issue was, though, that this number over here isn't divisible by 7, right?
Yeah.
Yeah. So in this case, we can actually, again, cheat a bit, and instead we should get close to a number that is divisible by 7. So we know that 7, so let's see. What would be divisible by 7? We know 1,400 would be, let's see.
1,743.
It is, I believe. I just don't know how to check that off the top of my head. 1,740, yeah. 1,743. So 1,743 is divisible by 7. So we can just do a bit of replacement over here. 1,743 plus 1 right over here. And if you're doing plus 1, what is that equivalent to? It's equivalent to multiplying by another 2 over here. Make sense?
Yeah.
So let's see. So this is congruent to 2 to the 7th power times some number, which according to my notes over here is 249. But again, it doesn't matter because that's just going to be, what is 2 to the 7th? It's just 1. So times 2. So this becomes 1 to the 249th times 2, which is just a really fancy way of writing 1 times 2, which is 2 mod. And I should put in mod, technically to be right, I should put in mod 127 all over the place over here. All right, so again, so we see that basically if there's not a direct solution, we just try to essentially get to our direct solution. We just simply take a step to try to get to our direct solution. All right. Now, let's see. So the way your computer can so let's go ahead and let me see. Should we do the next one or? Okay. Yep. So, right. Yeah, we can do the next one. We can try to do the next one, and then we can go through the slides to talk about this. So the next problem was problem was problem 7, which is find the units digit of 287 to the 3503. Nice giant big power. So first off, what is this question asking in terms of that's applicable to this lesson? Mod 10, right? The units digit is mod 10, right? Yep, so it's asking what is this? Mod 10. So how can we simplify this? So what's the first step to simplifying this? Can we calculate anything over here mod 10? Remember, when we're doing this, we can basically we can do this congruence wherever. So what about this? 287. We can calculate that mod 10 quite easily, right? What's 287 mod 10?
7.
Yep. So this now becomes 3,503 sevens multiplied together. Mod 10. Okay. So, but now figuring out from here is a bit trickier, right? But what we can do is that we can figure out how do progressive exponentiations work in mod 10. What I mean by that is let's go ahead and figure out what is 7. So 7, 0 would be obviously 1. 7 to the first power gives us, 7 to the first power mod 10 yields 7. 7 to the squared power, that's 49, right? Yields 9. Okay, that's where it gets a bit trickier here, okay? 7 cubed mod 10. But that's, so this is actually not so bad though. It's congruent to 7 squared times 7 mod 10. And remember the substitution rule. We can substitute anything we know anytime we want to. We know what 7 squared is over here. It's 9. It's not, so this would be 9 times 7 mod 10. 9 times 7 is, let's see, so that's 70 minus 7, which gives us 63. So this is congruent to 3 mod 10. Make sense? So, and now once more, 7 to the 4th power, we can use the same trick. Okay, and I know my notations, I'm probably butchering notation here. In fact, I'll just be correct and add in that at the end, the mod 10 at the end, rather than taking up all that space. 7 to the 4th power, we can rewrite as 7 to the 3rd times 7. We know what 7 to the 3rd is. That's 3. Okay. So let's see, that's 3 times 7, which is congruent to 21, congruent to 1 mod 10. And if we do now 7th to the 5th, which would be 7 to the 4th mod times this, which is congruent to 1 times 7, gives us 7 mod 10. So in other words, we're now in a loop. Because 7 would go to 9, 7 times 7 is 49, which 9 would bring us to 3, 3 would bring us to 1, 1 would bring us to 7. So, in other words, yep, 7 to the 4th. So we know, so here's what we do know. So why is this useful? Okay? Why is this useful? Because we know that basically 7 is that we could, if we can get something of this factor for some k, okay, 7 to the 4th k power, like ultra HD 7, I guess. All right, then that would be congruent to 1 mod 10, right? So again, we can use our trick, a bit of a trick here. We know that figuring out, we've got a big number here. We've got, let's go, and we've got 3,503 though. But that can be split up into, I mean, just off the top of my head, right? One of the nice things about 4s is that they generate hundreds. Okay, so 3,500 plus 3. We know that, and we know this is divisible by 4, right? So what we can do is that we can go back now to our initial problem statement, okay, of 3,503 is congruent to 7 times 3,500 times 7 to the 3rd, and we know since this is a multiple of 4, since we know that 3,500 is a multiple of 4, that we can simplify that down to 1, right? Because it's congruent to 7 to the 4th times 7 to the 3rd. And we also know what 7 to the 3rd is, by the way, because we calculated that. It's 3. And so if we can actually check this one by using some very nasty math by opening up IDLE. And IDLE is all sorts of fun. 287, let's see if it even does it. 287, bang bang, or star, 350. By the way, that's how you do exponents in Python. You do two multiplication operations rather than using the caret symbol, which is used for exclusive OR, I believe. Exceeds the digit it exceeds the max number of digits. So there is a max. Cool. 4,300 digits apparently. So yeah, can't really check that, but I can pretty much guarantee that it is 3. Oh yes, forgot to add the important bit, mod 10. Again, I'm not a mathematician. I just cosplay as one. All right. So let's go back to the slides for a bit. Okay. And again, I'm sorry that you're also being subjected to like my beta test of this class. This is the first time I'm running it. So it's going to be a bit rough around the edges in terms of figuring out what the best time to present stuff is, how much I go into detail about that. But if you are finding you're confused by something, please, I'm more than happy to spend more time on it. So modular addition. So let's talk about some facts about modular addition now that we can just kind of know. So going back a bit more to basics. So we know that, okay. So let's see, since x and y are each in the range of 0 to n minus 1, their sum is between 0 and 2 minus 1, 2 times n minus 1. I mean, that makes sense, right? If we're working in modular space, like we're saying we're working in mod 11, right? If we're working in mod 11, the two biggest numbers we can add that have any kind of meaning is 10 and 10, right? And that would generate 20. And that's going to be between this state, so 2 to the 10, so 2 to the 11, so 2 times 11 minus 1, so it's going to be between 2 and 20. Sorry, it's going to be between 0 and 20. Now, if we do have something that exceeds that n minus 1, which we did in this case, you just simply subtract off n, and you get back in the range, right? 10 plus 10 minus 11 brings us to 9. You know, and you can do that operation in your head as well with the, you know, what is 20 mod, what is 20 mod 9? That is equal to 11. Sorry, 20. Well, that's true as well, but I meant to write what is 20 mod 11, and that gives us 9. I don't know, wouldn't have been true. I just simply wrote in reverse. So what it's saying over here is that we just simply need an addition and a subtraction. So in other words, it's, again, a linear operation because we're just doing an addition and a subtraction. Where n is, again, the number of digits with that of log base 2n because we're converting. It's saying basically n is the number of bits. Let n be a decimal number in this case, so log base 2 because whenever we see a log, this is saying basically it's just going to be linear to the number of bits it takes to do an addition operation in modular arithmetic, just like adding any other number. Make sense? Because all we're going to do is add a number and possibly subtract a number. So 2n operations, essentially. Or 2 O of n operations. Because, again, what is subtraction but just... and again, we didn't go over how computers do... I didn't explicitly say how computers do subtraction. But I'll say it now. Explicitly, the way computers do subtraction is that they just simply add the negative. It's just subtraction is just addition. Spicy addition, if you will. All right. Similarly, for multiplying these numbers, it's also quadratic because, again, if we multiply these two numbers, so again, if we take our mod 11 example and we multiply 10 times 10, we get 100, okay? The product can be as large as, you know, as 11 minus 1 squared, it is, but it's still at most 2n bits long because we are going to, because it's math again, 2 to the equal, so because 2 log of n minus 1 squared is equal to, when we do that squaring operation, we bring it down to the 2 log n minus 1, and that's going to be less than twice the number of bits. Less than or equal to twice the number of bits that we need. So again, what we do is that we, reduce the answer, and after we get our multiplication, we can convert it into, after we do this multiplication in modular space, we just do our normal multiplication, okay? So if I want to multiply these numbers x and y, then all I have to do is actually just do multiplication by like normal, and then to reduce it, I do exactly what you'd expect. I do division, but instead of asking for the quotient, I ask for the remainder. So we will get to modular division, not today. It will not be appearing in this episode because it's different, right? In normal arithmetic, we only really care about one possible operation that could really muck things up, which is dividing by 0. But with modular arithmetic, it can be a bit tricky because of modular inverses. So you were talking about me using the prime notation earlier. The book uses this notation basically to denote that if we have some number a and we multiply it by a to the negative first, that is we denote this as like as its inverse, as the modular inverse, which we'll be getting to later. Division's only really legal in those cases, and when it is legal, n cubed, and takes n cubed time to do modular division, which, again, number of bits is, where n is the number of bits. Okay, so as we were talking about, as I mentioned a few times, RSA, which is the crypto system we're going to be learning about, the computer needs to be able to calculate x to the y mod n, where x, y, and n are all hundreds of bits long. And as we saw with our poor Python computer, when I tried to ask it 2 to the 87th to the 3503, it just kind of croaked on us. It just gave up and threw in the towel, at least for that. Use set string int max digits to increase the limits. So it is possible. It is possible for you to just go in and modify how long that is in Python. But the result is, if it's mod n, then it can be a few hundred bits long itself. But as we can see here, right, we were just doing, so this gets us into an interesting conundrum, right? Going back to here, 287 to the, let's go ahead and explicitly ask for the answer that I want. More than happy to give that out. The issue was converting ints to a string. That's what the issue was. But as soon as I said here, it did all this computation over here, okay? It did all of this massive computation just to spit out something that's only a few bits long. Literally a couple of bits. It's 1, 1. So the issue is that, x to the yth power can be really big when the answer we need in mod n is going to can be comparatively small. Make sense? So yeah, even when x and y are 20th bit numbers, are just 20-bit numbers, that means that x to the y is at least this big, right? A 20-bit number raised to another 20-bit number is going to be pretty darn big, 10 million bits long. We don't want to calculate all those bits. Instead, we wanted the computer to do what we've been doing, which is cheating. We want it to be able to, substitute things. So to make sure, in other words, what we're going to do, we perform all those intermediate, we do the modulo. So we do what we were doing for on the whiteboard over here, which is that we do all these computations. Rather than calculating this, rather than calculate 7 raised to the 3,503rd power, rather than doing that, we're going to start at 7 to the first power, then mod by 10, then go to 7 to the second power, then mod by 10, then go to 7 to the third power, then mod by 10. So we keep multiplying by 7 and then modding by 10. So what we want to do here is if we want to calculate x to the yth power, we want to do x, mod it by n, then multiply that by x and mod it by n, then multiply it by x again and mod it by n, so that we always have a result that's small, right? More smaller than just computing it directly. Okay, so x to the yth mod n. So the individual multiplications in this case, we've got y of them, but they're not going to take too long. But they say, imagine if it's 500 bits long. Okay, it's still going to be painful. So here, what we do is that we are going to instead try this. X mod n, then we do x squared, then we square that result, then we square that result. Then, in other words, we keep squaring m doing mod n. Rather than multiplying, which increases the exponent by 1, we're going to keep squaring, which keeps doubling the exponent. Until we reach a point where we really can't, double it because we'd exceed that value, But it says, takes log base 2n time to compute, which citation needed on that. 1 second. Each takes log squared. This is a typo. This shouldn't be there. Each of these takes log squared n time. So log n times log n, time to compute each of those multiplications. And there are only, instead of there being y multiplications, there are log y. Now why log base 2n? Again, n is the size of this. Log base 2n is just a fancy way of writing n, right? And a multiplication takes n squared time. That's where it got the log, so it got the log n squared. It got this from the fact that, remember, n is our value. Big N is our value. N in this case is the number of bits. So this just simply said, yes, the multiplication, once again, is O of n squared. So here, though, rather than having to do, over here we were doing O of n squared, and we'd had to do y of those. Because we're doubling each time, we only have to do O of n times log y operations, as the slide says. So again, let's see. And so what it says over here is to figure it out, then what we do is that we can break it down into a binary representation. And those can be solved by doubling, so compute x to the 16th, x to the 8th, x to the first power. So the way that works is by doing this. Has a running time of O(n) cubed. Let's see, how much time do I have? To 35, right? So I'm debating whether or not to run that algorithm. If I want to, I'll run that. We will check that algorithm on Tuesday, okay? Because now we're going to get into what we're also going to be talking about on Tuesday, which is now why have we been doing all this nonsense? Which is the Euclidean algorithm. So Euclid of Alexandria, he lived about 300 years. He was about 300 years before the Common Era. And, you know, since his name shows up in math a lot, I guess he was important. No. Let's see what he was. Let's see all the things he was famous for, because it's a lot. Right? Right? Euclid, Greek mathematicians, geometer. Right? Euclidean geometry. When we talk about the space we typically work in, we're talking about Euclidean space. You know, this is. And that's generally an accurate enough representation of reality for a lot of things that it's a lot of times all you need. So a lot of stuff when it comes to geometry. Don't confuse him, by the way, with another person who starts with EU, which is Euler, also a famous mathematician. I've made that mistake before, but they're almost 2,000 years apart. Okay. Euler is more famous for kind of graph theory and other stuff, but also geography. Also, he has every single law seems to be named after Euler, or every single principle seems to be named after Euler. Like there's I don't know. Let's contribute. Eulerian path. There's the Euler. We're going to be talking about the Eulerian totient function. There's a lot of things. Name that he discovered. So but going back to Euclid, he came up, besides geometry, which is what he's most famous for, and I don't know why I was blanking on that so hard. He was also known for creating a bunch of algorithms, including figuring out what the greatest common denominator of something is. Okay. In other words, how do we figure out what the greatest so in other words, what is the greatest common divisor, as it's also sometimes called? When I was learning it in between 4th and 10th grade, it was the greatest common denominator, and at some point it became the greatest common divisor. I mean, it's the same thing, what it comes down to. Basically, the biggest number that divides both these things. So now, here's the thing. The way we would want to do this, if we've got like two numbers like 1035, it says over here, and 759, and we want to figure out what their GCD is. The obvious approach to do is to figure out what their factors are, right? And it does the math for us that 1035 can be broken up into 3, another 3, a 5, and a 23, okay? And 759 can be broken up into a 3, 11, and a 23. And so you just multiply together the factors they have in common, which are a 3 and a 23. Make sense? So their greatest common factor would be 69. However, factoring is terrible. It is terribly hard to factor. In fact, we rely on the fact that we hope and pray that every day that factoring cannot be done in an efficient amount of time because we rely on that for security, as we'll see. It is one of those kind of NP, those are problems that are in NP complete. And so, yeah, it's very good that factoring is hard for that, for security reasons. So, but factoring is not, but greatest common denominator isn't factoring. It is greatest common denominator. Is there a way to get that faster than exponential time, essentially? And the answer is that Euler had this rule, which is that if you've got two integers, x is greater than y, and for this one, again, if the reason we say x is greater than y is because it makes it easier for us. If one is bigger than the other, if y happens to be bigger than x, you just swap them. Okay, so, but for this purpose of argument, x is bigger than y. The greatest common denominator of x and y is equal to the greatest common denominator of x the remainder if you divide x by y and y. Or there's a simpler rule where if you just simply do x minus y and y. Any integer that divides both x and y, so in this case we saw any integer that divides both x and y, 10, 57, and so we saw that 69 divides both of them, right? It must also divide this number, 1035 minus 59. Calculator, again, to do the math for me because I'm not going to do that in front of the class and waste your time or make an embarrassing mistake like that. 1035. I say as I mistype things. 759, 276. So we're saying that that number, that 276, is also divisible by 69. If we check, is indeed divisible by 69. Any any number that divides both x and y must divide x minus y as well. Okay. Any number that divides both x and y must also divide both x and y. So basically, it's one of those proofs that is fairly straightforward. You can check them for yourself. But what it is that here's the way our algorithm works. Given greatest common denominator, a and b. Okay? Again, those kind of proofs I wasn't really focused on when I was preparing for this. It was more nailing the Euclid's algorithm and the extended algorithm. Okay? So we've got two integers, a and b. Our output is the greatest common denominator of those two things. If b is equal to 0, return a, return, wait a second, this is what he put down, b, comma, a mod b. Didn't he say it was x, y is equal to the greatest common denominator, x mod y and y? We're swapping them. Why are we swapping them?
Order doesn't matter.
Order doesn't matter for the purposes of figuring out what the greatest common denominator is, right? The greatest common denominator of x and y is equal to y and x. So why are we swapping them here?
And when we do like a mod b, the result of a mod b is less than b, so to continuously rise.
Right, that's exactly right. The idea here is that we're always going to put the smaller one, we want to put the smaller one on the right side. And just by doing the modulo operation, A mod B is always going to be smaller than A or B, right? So we need to put it on the right side. So we need to put it on the right side so that we can always have on the recursive call the bigger mod the smaller. It's not useful for us to do the smaller mod the bigger because that's going to give us the same answer no matter what. Okay. So let's see. So what we're going to do, and it says, by the way, if A and B are both greater than 0, then A mod B, it's going to be half of the value of it, that the result is going to be half of our bigger value. It's going to be, or rather I should say, it should at least have our biggest value. And you can read up on the proof yourself, but let's go ahead and before we do that, I want to run through this algorithm before we run out of time. Make sense? And then we can come back to doing proofs next time after I've had an appropriate amount of time to look at them. Because, again, I was focused on the algorithms because this is an algorithms class. All right, and this is definitely one that you would see on a quiz. Okay. So we've got, let's go ahead and put this here. Put here. Let's go ahead and change our color to make it distinct from everything else we were doing. Okay, and now we've got, okay, we've got two numbers. So let's go ahead and calculate our two numbers here. Yeah, let's go ahead and do 20. Let's do one that we'll see a few times. A is equal to 25, B is equal to 11. Nice and easy for us to compute. They're not too big numbers, right? So we pass in A and B, all right? So in this case, what we want to return is, so if B is equal to 0, it is not. So now return B, A mod B. So what is A? So I should write down 11 because that's what B is, not B. So what is A mod B? 25 mod 11 is 11. 11 would be 22, so this would be 3, right? 25 mod 11 is 3. You can check by adding 11 to that, getting 14, adding 11 to that to get 25. Now is B equal to 0? No, it is not, so we write down 3 over here, and we do 11, and then we do 11 mod 3. 11 mod 3 is almost a 12. It's 1 away from 12, so it's got to be 2. Is B 0? No, it is not, so we compute 2 over here, and then we do A mod B, which gives us 3 mod 2, which gives us 1. And now we've got 2 mod 1. So that would give us 2 mod 1, which means put 1 over here, and then we do 2 mod 1, which is over here, that's 0, because anything mod 1 would be 0. So now, if B is equal to 0, return A. Okay? So we return A, and now we return A, and that gets passed, and that's what gets returned all the way up the chain. Okay, so, and you can check that, 25 mod 11, 25 and 11, they don't have a common denominator, right? Let's check it for something that does. 30 and 25. We all know, we can see what the common denominator is just right off the bat, it's 5. Okay, but let's run through this. 30, so is B 0? No. 20, so we put 25 down here. A mod B is going to be 5. 5 is going to be, and so now, let's see. So now we're down here, 25, B is not 0. 25 mod 5 is going to be 0, so we pass in 5 and 0. is B equal to 0? Yes, it is. So return A, which would be, and the return calls are all the same. It's return what we just passed into each other. So it works. And we can and so let's take a look at that runtime for a second. So A becomes 20, A becomes, so we start with B. So B is our thing that gets modded. We start at 25, and then we get 5, and then we get 0. That shrank very quickly, very, very quickly. So if B is less than or equal to A1/2, there's the math there, but basically again, I will review this proof and so I can better explain it on Tuesday for you. So the next step we're going to do is something called, so why are we caring about this? We are going to care about this because we want to figure out something that we want to know, we want to be able to check if something is the greatest common divisor with something called the extended Euclidean algorithm. And we can get and what that can give us is that can give us an answer to a formula, which is, it gives us some number D that is that gives us the greatest common denominator, which gives us D, and it gives us that in a formula, which is AX plus BY. Why in the world will we want that? Great question. And the answer is to be able to find, and the answer is because I said, hey, let's leave division to later. And the answer is we need to be able to do this Euclidean algorithm, as we'll see, to do division by calculating the modular inverse. And that will be basically the end of once we get through that, we'll get to the end of starting to do our modular arithmetic, and then we're going to talk about primality testing, which is kind of the inverse kind of check of testing if something is prime. Which is different problem, but similar to factoring. So let's go ahead and check the homework briefly, okay? Okay, and see what we can do, and I can adjust as necessary. So this talks about binary, converting from binary to decimal. How long does it calculate, analyzing the recursive algorithm, taking a look at the division. So it wasn't a homework question, and I did tell you that you want to kind of use mathematical induction to prove 1.8. Okay? And again, so do you need a refresher on mathematical induction? Proof by induction?
Yeah, we learned about it.
You've learned about it?
In computation or something.
Do you want a refresher? Okay.
I'm okay with that.
All right, so I'm going to go over one of the more famous things for mathematical induction, which is proving an infinite series. Okay? Mathematical induction and recursion are they're really kind of two sides of the same coin. You use mathematical induction a lot to prove how that a recursive function is true and will be successful. So let's go ahead and see something that you're going to see that we see a lot in runtimes, which is 1 plus 2 plus 3 plus 4 all the way to n. Okay? Now, one of the things I check is I often ask, what is the big O runtime of that? And the instinctive answer is n, but it is not n. It is O of n squared. And the reason is because Calc 2 is awful. So here is a formula that you may have learned in Calc, because there's a formula in Calc 2, which is, you remember it now? Yep, it is, rewrite that. I'm so used to scribbling things out rather than just cleaning I to the n, 1, is equal to n times n plus 1 over 2. Okay? You've probably seen that formula before. Ever get proved to you?
I think,
Yes. I think we have to prove it, right?
yeah.
You pretty much always have to prove this one. Have you seen it done by proof by induction?
Yeah, no, that's what I meant.
Yep, it's the classic proof by induction. Now, let me just visually represent this for a second as to why this is the case, visually. Okay, which is not a proof, but it helps, right? So we've got 1, we've got 2, we've got 3, we've got 4. You know, this is a square where essentially our runtime is taking up half of that square, a bit more than half of that square. You know, it's a triangle, a bit more than half the square. So kind of visually makes sense that would be n squared. Now this is a very common runtime. It's like when you're doing a nested for loop, but an efficient one, where basically you're like checking, where you've got a for loop and you're like saying, okay, let me check each item against every other item, okay? But rather than being inefficient and saying, I'm going to check 1 against everything and then I'm going to check 2 against everything, instead I'm going to say I'm going to check the first item against everything to the right, then I'm going to check 2 against everything to the right, because I don't need to check anything to the left of me, because checking A is equal to B is equal to B is the same as checking B is equal to A. That's why, I mean, you'll see this a lot. So the way proof by induction for this works is that you first prove a base case. You basically choose something as easy as possible to prove, which is that in this case we're going to show that that this works for 1. So this is the sum of 1 all the way up to n is 1 when n is equal to 1, right? And plugging in for 1 over here is 1 times 1 plus 1 over 2. This is a fancy way to write 2, which is another fancy way to write 2. Strike that out, it becomes 1. 1 is equal to 1. You know, it's, like I said, we choose an easy thing. So the key thing for induction is that second thing, which is assume true for some k. Assume it works for some k, and then prove k plus 1. So you assume it works for some k, and then you prove does it work for the next one before that. And the reason being is because since you've proved a base case, if you prove if it works for k, it works for k plus 1, you can start your base case and go, aha, since I know it works for 1, it's going to work for 2. And because I now know it works for 2, it's going to work for 3. And since I now know it works for 3, it's going to work for 4. It's dominoes, essentially, you know. So by proving this general case, we can say, starting from the base case, we know it's all going to work. So what we do over here is a bit of cheekiness over here, but 1 plus 2 plus 3 ... all the way to k plus 1. I'll go ahead and surround that by parentheses over here, okay? And that's equal to our original form. And now our original formula was n times n plus 1 over 2. So k plus 1 times k plus 1 plus 1. So everywhere there was an n, I replaced it with a k plus 1. 2. So now here's the bit that we get a bit cheeky, a bit smart, a bit clever, is that we assume that it's true for k, right? So we can use this identity as it relates to k. So we can replace 1 plus 2 plus 3 all the way up to k with k times k plus 1 over 2. And then we get k plus 1 over here is equal to, and now we've got our identity. So now it's just a matter of converting one to the other. So how do you do that? Multiply this by, what we're going to do is, let me rewrite that a bit cleaner, because my handwriting is terrible. Sorry about that. It's not just because I'm writing vertically. My handwriting is really that bad. I'm going to go ahead and multiply it by 2 over 2, which is 1. so that I can get rid of this, so I can get rid of that addition sign, right? There, and instead I'll put it there. Make sense? So now I've got everything over 2, so that makes that easier to prove. So now I've got k times k plus 1 plus 2 times k plus 1. And I'm going to do something that feels a little weird, but I'm going to extract the k plus 1. It feels a bit weird because normally when you like extract a common factor, it's yeah. Yeah, normally it's also in a different position when you extract it, so it feels a bit weird, but we can, so k plus 1, and so that is k plus 1 over here, k plus 1 over here, a 2 over here, a 2 over here, and we've got k plus 1 and k plus 2, and we can just simply rewrite that as k plus 1, because 2 is equal to 1 plus 1, as we were so proud to tell our mothers in first grade. You know? So that's a proof by induction.
But I still feel a little weird, like writing the result of a proof.
Yeah, it feels a little weird, but that's why I like it so much, because it feels nice and easy. Proof by, I mean, the things we want to do in this class a lot are proof by induction, proof by contradiction especially. We love proof by contradiction because if I'm telling you to disprove something, the best way to do that is find something to disprove it with.